Good evening. Welcome and thank you for joining our TI Technology webinar hosted by Texas Instruments. Tonight's session is AP Precalculus, Develop Procedural and Conceptual Fluency Using TI Technology. I'm Ruth Casey and I'll be the host tonight. We're pleased to be joined by two fabulous, amazing educators, Greg Foley and Rachel Gorsuch. Um,
Hi, everyone.
Hi.
Hi, everybody.
Hi. Welcome. We'll let you share a little bit more about yourselves here in a minute. Right now, I want to get the chat function going here. We will be using the chat feature, so find that panel if it's available on your device. And if you'd like to try it, send a chat out to everyone. Let us know who you are and where you are this evening or afternoon or morning, wherever you are. And if you want to put in the temperature where you are, that'd be interesting to find out as well. Be sure to check to select everyone from the drop-down menu. As a reminder, the session is being recorded and will be available for viewing or reviewing the presentation. If you experience any audio or video issues that can't be resolved fairly quickly, please feel free to watch the recording later. And at the conclusion of the webinar, you'll get a link with a certificate of attendance and also a link to documents for tonight. And then via email, the email that you use to register, in a couple of days, you'll get that certificate of attendance link again, as well as a link to the documents. Rachel, Greg, welcome and thank you so much for being here.
Thanks, Ruth. Okay. Why don't you start us off here, Rachel?
Sounds good. And I was just reading through all the chat. I hope we stay this busy on the chat the entire time. Although you all are starting to make me cold, like I'm going to pull my sweater in a little bit. We are pretty cold here in Ohio, but it looks like even the deep south, you're pretty cold as well. So introductions, my name is Rachel Gorsuch. I'm here in Columbus, Ohio. I'm a high school math teacher. And Greg, do you want to do a quick introduction of yourself?
Yeah, I'm based in Athens, Ohio, and also split time in Austin, Texas. I teach at Ohio University. I've done a lot of summer professional development for teachers, and I'm really looking forward to digging into some pre-calculus tonight.
So we're going to be going through this agenda tonight. And as you can see, it's all about solving equations, thinking about things using technology, using algebra. All of these things are married together to make this AP Precalculus student successful. So hopefully we give you something to think about as we go through this webinar. We will have a webinar drawing at the end for a free calculator, and Ruth will help out with that part. We do hope that by the end of this webinar that you feel that you're capable of doing the things that we have here on the screen. And I'll give you a moment just to read through those, but we want to give you a chance to experience functions in multiple ways tonight. As Ruth said, we're going to be using the chat quite a bit, so feel free to keep putting questions, thoughts, suggestions in there for your fellow colleagues. We're all learning from each other tonight, and Greg and I are both going to be keeping an eye on that chat. So I thought, what better way to start a webinar about AP Precalculus than to take an excerpt from the CED and see what the course is really supposed to be about. So this is from page 6. I'm going to give you a moment to read through it. And as you read through this, I'd love to see you put in the chat, what do you think stands out to you most about this paragraph in the opening part of the CED? So I'm just going to give us a moment to read through this, and I'm going to keep an eye on the chat as you start to add your thoughts.
Right. And As you notice things in this paragraph, is there anything you're wondering about? What do they mean, or how would I implement that in my classroom? Go ahead and put that in the chat too.
Thanks, Greg. Jenny's getting us started, Greg. She noticed that in this paragraph, they're talking about 4 representations of functions being graphical, numerical, analytical, and verbal. And that the idea is we're going to try to widely apply math to situations. And I'm noticing, Greg, as I read through the chat, more and more people are really starting to point out those things that you underlined, the graphical, numerical, analytical, and verbal. And Kimberly, she's thinking like you, Greg. We were just talking about this before we started, Kimberly, that they do seem connected to the math practices, which is our next slide, that if our students are really understanding these functions in multiple ways, then they're going to have this procedural and symbolic fluency. They're going to have the second math practice, which is multiple representations, and they're going to be able to do that third math practice of communication and reasoning. Yeah, definitely the communication and reasoning piece is something that in a traditional pre-calculus course, it might or might not have been highlighted depending on the teacher. But this course, as a course, is saying this is going to be a real priority for us.
Right.
Lots of foundational knowledge to apply to future coursework. I agree, Derek.
Right. The Chinese talk about the 2 basics being conceptual understanding and procedural skill or procedural fluency. And I think the AP really links those 2 together, that the kinds of questions that are asked often will require students to complete a procedure, but it's also sort of testing their understanding of some related concept at the same time. And so if you can teach in a way that links procedures with concepts and understanding throughout the course, it's really going to benefit your students.
So Greg, I love that we got the chance to talk about the math practices. I just wanted to touch on them real fast. You can find these in the CED as well. But I don't want to take away from the technology tonight. I know that we could have lots of great conversations about the math practices, but I have one more question before we start pulling out calculators. And I think that's on the next slide, Greg.
Okay.
So this is a question that I've been thinking about a lot with my colleagues. I'm curious about what methods or tools we all use as mathematicians to solve equations and inequalities. And just one step away from that question, I have another question. What methods or tools do you teach your own students to solve equations and inequalities? And as we ponder our answers to those 2 questions, do they match? So are the tools that we use as mathematicians the same as we're teaching our students? And I'd really love to get some thoughts in the chat, either about the first question of how do you solve things as a mathematician, or how do you teach your students to solve them? Are they the same methods that you're using yourself and teaching students? Or are they different? And is there a reason for them being different? So I'd love to hear your thoughts. Kimberly's saying that now, Kimberly, I'd love to get your follow-up on this. Are you saying that you solve things algebraically, tabularly, graphically, or do you teach your students to do that, or a little bit of both? I love to hear that you do both.
Yeah, I know sometimes at the college and university level, um, faculty are guilty of really having students focus on sort of low level skills and but in their own work, in their own research, they're using computers all the time, but they may not let their students use calculators and computers and technology in the classroom. And so I think what Rachel's driving at here is if we're using certain tools to do problems, especially more complicated problems, then maybe we should have our students engage in the same kind of tool use that we use.
And I noticed Kristen saying that she kind of starts graphically. I do the same too. I often make sense of problems graphically and then go and support with algebra, even though that's kind of the opposite of the way I teach my students. And I've been trying to reflect on this through this course of why I'm doing these certain decisions that I'm making. And I'm seeing that Phyllis is suggesting show them multiple ways and then let them make that decision of what they think is the most comfortable.
Okay. Well, with that prelude, I think we're really in a good spot to move on to example one. And let's take a look at this. This is very much an AP kind of wording to the question. The wording on the AP exam, especially the free response items, is often very cagey or tricky or subtle. And here we've got at the right two functions, graphs of two functions. One is f of x equals x squared minus 3. So would your students be able to identify which one is x squared minus 3? I think they probably could. They could bring that skill in from Algebra 2. The other, G, passes through the points 0, -1, and 1, 0. So what are the solutions of this system of equations? So here we're given graphical information. We're given some algebraic information, right? We have this algebraic information. We're also given some numerical information, and things are put in sentences. So we have really verbal, graphical, numerical, algebraic, all going on at the same time. What is the red graph, that function G? Well, I'm going to switch on over to the TI-84 CE here. So I'm going to stop sharing this screen for a minute, the slide deck, and come on over to the calculator and share that. Hang on just one second.
And Greg, while you're
Pull-
pulling that up, I would just want to give voice to something that Michael said, that we as teachers are able to use tools that sometimes pre-calc students either don't know or they're not ready for. So that's one of the reasons that we need to show them multiple ways of solving problems so that they have these multiple tools as well.
Okay, so this graph looks much like what we just saw. The only difference is I had actually squashed this because I wanted the scale of 1, 2, 3 on both axes to be the same. So when I created that image, I went to a zoom square feature, which is zoom 5, and then I actually just chopped off the middle part of it so that we would have sort of -10 to 10 in both axes directions. So now that you've seen a couple of versions of the graph, uh, are you ready to solve this system of equations? Or would you like more information before you solve this system? Go ahead and chat. What would you like me to show you from the 84 maybe that would tell you a little bit more? I mean, I could show you, for instance, what the window is here when we square it up, if you think that will be helpful, or um, we could trace along the graph. And in here, when we trace along the graph, I guess it's giving us that formula for y1, and it's showing, what we can trace to. And if you wanted us to trace to a particular value, we could say to enter and see what's going on there. It looks like there might be a point of intersection there. We could enter -1 if you think that maybe there's a point of intersection there.
So Greg, they've said that having the scale for the markings is definitely important, which we were kind of able to see that from the window. But Monica says she wants to see a table of the values of this graph.
Okay, so let's see. I'm going to go to table set and see what we've got here. Negative, starting at -5. Looks like that might be okay. Let's give that a whirl. Oh my gosh, what in the world is this? It says error under y2 for x equals to 2. So it looks like at when x is -1, both y1 and y2, both f and g have an output value of -2. So we do have a point of intersection, but something crazy looks like it's going on here. What else would you like to know now? Would it be helpful to know the formula that's driving y2?
Yeah, Michael's hypothesizing that it's a rational function of some sort.
Aha! How right you are. So this is a rational function, and so we got x squared minus 3x plus 2. And this I think we could factor fairly easily. Now I don't have this on my iPad, so I can't annotate it very well, but this would be, I guess, x minus 1 times x minus 2 if we factored it. So there's an x minus 2 factor in both the numerator and denominator. So this is what would be called um, a removable discontinuity or a hole in what would otherwise be a linear graph. So this graph's much like x minus 1, but with a hole when x is equal to 2. So we've got a wonderful feature on the 84 called Zoom Decimal, which I don't know how many of you use this with your students, but this allows us to see what's happening at whole number values and at nice decimal values like 0.1, 0.2, 0.3, and so on. So if we graph it that way, if you look very carefully, you might notice this hole in the red graph. It'll be more obvious if we turn off the blue graph, if we turn off F or Y1 and look at just Y2 or the graph of G. You can see that there is a hole. And when we trace in this decimal window, we're tracing and we get, x is 1/2, 6/10, 7/10, 8/10, 9/10, 1, and so on. And when we get up to 2, the y value disappears. So in the table, remember what it said? It said error. So in the table, it shows up as an error. In the graph, it shows up as a hole. And in the algebra, it shows up as a common factor in the numerator and denominator of this rational function. So this is a concept that honestly, I think I passed over pretty lightly in teaching pre-calculus in the past, but this is more of an area of emphasis. So you can't spend days on this, but every once in a while you can have students encounter a problem to remind them of this concept of a removable discontinuity or hole and what the implications are. So there's really only one point of intersection. The table of values was a very good way of seeing this. So having multiple representations, having graphical, numerical, algebraic, and connecting those representations and getting students to make connections is really crucial in AP Precalculus. So I'm going to try to get back to our slide deck and see what's next on the agenda here. Probably example 2, if I can find it here. So let me share I'm actually sharing my iPad, which allows me to do annotations. So it's going to take a little bit of time, I think, for that to come back up. Do you see it now? Yeah. So now, in this second example, it's the same two functions. And here, if you look real carefully, you might see that there is a hole here, and that there's an actual point of intersection. And this point of intersection would be at -1, comma -2, right? And here, there is no intersection. The blue graph has a functional value, but the red graph does not. So what equation is associated with this system of equations? Well, one way to write it would be, I guess, to say f of x equals g of x, right? And f of x we had was x squared minus 3, and g of x was this crazy function with the whole. So it's sort of x minus 1, but then multiply numerator and denominator by x minus 2 to create a whole when x is equal to 2. And so solving this equation, we could multiply both sides by x squared minus 1. So this is a case where you might have extraneous solutions, right? It would be the concept in solving a rational equation. When I teach, and I think when most people teach, we probably start by not with solving a system of equations. We probably start by solving an equation. But we often turn this equation when we're solving something like x squared minus 3 equals some rational function. We might graph the left-hand side and the right-hand side and look for points of intersection. So we've really, when we solve graphically, a lot of times we turn a regular equation into a system of equations. And maybe we don't think about that explicitly as that's what we're doing. So one way to make this a single equation or a single function would be to take this, in the second question, how could you rewrite this? We can always take f of x minus g of x, the left-hand side minus the right-hand side equals 0, or I guess on the calculator it might be y1 minus y2, and we could see what are the zeros of the difference. And so if you remember on the agenda, it's like, how can you make new functions from old? If we have functions f and g, we can look at their sum, their difference, their product, their composition. We can take functions and combine them in, through various binary operations. So again, I'm going to have to stop and start again. So let's see if I can share my calculator screen again. And so what I might want to do then, we only have one function chosen right now. Let's go back to our y equals menu, and let's turn off y2 by pressing enter on the equal sign, and then turn on the difference between y1 and y2. Press enter, and let's graph that and see what it looks like. So maybe this is what you were expecting. I probably should have paused before I press graph to ask you what you would expect. But as you notice here, we've got we've got a point of intersection here, which we could get to by trace, and just typing in -1 is where we have a 0 of the function. And that's the same x value where we had a solution to the system. And what happens if we say to enter? Again, we get no x value. If either of the two functions is undefined when x is equal to 2, then the sum or difference or product or quotient would be undefined. It gets a little bit trickier to do compositions of functions. Let's think about this a little bit. We could compose in one of two different orders, right? We could enter. We could compose first running it through the rational function and then running it through the quadratic function. So before I press graph this time, I am going to ask you to think about what should this graph look like? Y2 is sort of a linear function with a hole in it. It's a rational function, but it's very closely akin to a linear function, but with a deleted point. And then this is a quadratic. And so we would be running x through the linear function. Would this be undefined for any values of x?
If you guys could put that in the chat, we'd love to hear your thoughts.
So is this function y7, which is y1 of y2 of x, is that going to be undefined for any x? What would the domain be? Okay, I'm going to go ahead and graph it. You've had time to think about that now.
We're anticipating a hole at x equals 2.
And sure enough, there is a hole at x equals 2. And we've transformed this upward opening parabola. It's been shifted. To the right, hasn't it? It looks like the minimum is still at 3. So we have a shift to the right plus a hole being poked in the function. Now, what if we go the opposite direction in our composition? Would this be a different sort of thing? So part of this symbolic manipulation or procedural understanding that they're trying to get us to have in the AP curriculum is to understand composition and all this sort of thing. So now we start with the quadratic first. We run this through the quadratic, and then we run it through a linear function with a hole in it. We run it through a rational function. So is this going to be undefined anywhere?
So Greg, we're gonna just give ourselves a second to catch up with the chat because there's a lot of great things that are coming up. For instance, Mary Jo said that she just taught composition of functions and didn't realize that you could graph the composition of the graphs in this way. And I think it was Vira was saying, and I apologize if I said your name wrong, but was saying this is really great that on the 84 you can use that z decimal, and we do want to make sure that's clear. It's the z decimal that is showing this hole, and it only works at like each 10th. It's not a perfect system, but it is a great feature with the z decimal. Now, Greg, I do want to make sure, because this was something you taught me in the past year. Where are you getting those Y1s, Y2s? Because especially for all of these things
Yeah.
with the subtraction, I think that that's something that teachers could save a lot of time with button pushing if they just knew where to get those.
There
Those
is a
function
shortcut
names.
now. So if you press alpha first, then you can press like alpha trace and you'll notice not only do you get the y variables, but you would also get matrix functions if you press the third key. You would get so you can actually, I think you can go left and right on this. Once you get in here, you can use the left and right arrows. So you have quick access to fraction menu, to various kinds of functions.
Including all those logarithms.
You can do on the fly matrices, create a 2x2 matrix, and then just plug in the numbers you want on the home screen, which now that I'm teaching linear algebra, that's a fabulous feature for me. And then this is where I got those. Instead of having to say vars, y vars, second function, like 4 or 5 keystrokes, this is 2 keystrokes, alpha, and then trace. And if you mess up and you say alpha zoom by mistake, you say, oh, I want y bars, I can just use my right and left arrow keys to get to the menu that I want. So that's the shortcut.
Yeah.
Um,
Those
that
green
alone is
commands,
worth the
those.
price of admission, maybe.
It really is, because I'll tell you what, I've had students spend a lot of times just trying to type in rational functions. And if I could do a parabola and a linear function and help them see how these are all related through these connections and these y vars, I think that I could use my time really effectively as a teacher, but also make the connections much clearer.
And do we have a hole this time? There's no visible gaps. So we have, it looks like we might have a polydent commercial here. No gaps, no letting go. But let's zoom out and see, maybe we've got something. I've got my zoom. Another little zoom trick is I like to set my zoom factors instead of the factory settings. I like to set them at 2 so that it zooms out more slowly than a factor of 4, which is the factory setting. So I'm going to say zoom. I'm going to zoom out to see more of the graph, and it's centered at the origin. And when I zoom out and press enter here, do I see a hole anywhere? Well, let's think about this algebraically. Um, what would cause this function to equal 2? Is there any number x that would cause y1 to equal 2 and therefore y2 to be undefined? Well, we could solve a little baby equation, set this equal to 2, which means x squared would have to be 5. So maybe the square root of 5. So let's go back to our graph, press trace. How the heck could I get to the square root of 5? I say, oh, I remember that it's about 2.236. Well, that's really not close enough. It's still going to give me a functional value there. I'm going to actually have to say something like second square root and type in 5. And then when I press enter, it actually says, nope, there is no y value. And actually, I believe negative the square root of 5 would do the same thing. So I could say the opposite of the square root of 5. And again, there's no value. Now, one way you could get this to show up maybe would be to center the graph at the plus or minus the square root of 5, and you might see a hole there. But
Greg, I'm just going to interrupt for just a moment. I apologize, but
Mhm.
Michael was asking that question of why were the gaps so obvious on our previous gaps, but not on this one? And Michael, it really comes down to that Z decimal is basically turning on and off pixels. So it can only do it at every 10th, every perfect 10th. And since we're using the square root of 5, it's just not as perfect as a number.
Right,
Now I think it's perfect. I have nothing against the square root of 5,
yeah.
but for graphing, it's not going to show that
So,
whole or that removable discontinuity as well.
right. So the points that are being plotted are these ones that we're traced to, and then the calculator connects in between. Um, and so the point at square root of 5 is not being plotted. Um,
Greg,
and
we have
so
a question. Can we zoom in on where we think the hole is? It would be kind of fun to see if we can see it or not.
let's see if we can zoom in, and I'm wondering if I can type the square root of 5 here to be the center of my zoom, if it'll let me do that. But no, it jumps to the home screen. So let's zoom in again. I'm going to say zoom in, and the best we can do is 2.2, and we could enter and zoom in, um, and we can go till we're blue in the face. But since this is a non-repeating decimal, it's a irrational number. Uh, we're going to be plotting x values that are um, rational, not irrational. So we'll never have that very point of square root of 2 in our window. If there's some way we could center our window at square root of 2, so maybe we could do something like this. Let's see if this works, because there is interest. Uh, how can it's not showing me my window. Maybe I'm still in okay, let me try to go back to window. There we go. Suppose I say, 1 plus the square root of 2, or square root of 5, excuse me. And then, whoops, I think I did that backwards, didn't I? I want I want this to be 1 plus the square root of 5, or the square root of 5 plus 1 might be the better way to say it. And I want this other one to be the square root of 5 minus 1. So we're trying to put the square root of 5 as our center value. Um, so this is not something I've ever tried, but what the heck? Let's see what happens.
I know, I'm curious about it. And the fun thing about this for me is so often my kids come straight from physics where everything has to be rounded, and I love my physics teacher.
Yeah.
And then they come into math and they're like, why can't I just round everything? And this conversation right here is exactly why we have um, these actual rational, or these numbers written as irrational numbers, because they're precise.
Right. So if we look and if we want to know what's really being plotted, it's a number that's very, very, very close to the square root of 2, 2.236. I'm going to subtract and just show that maybe there's yeah, this is it. This is the number that's being plotted, and it's uh 10 significant figures. There's 9 places to the right of the decimal point. So it's not plotting the square root of 2. It's plotting something that's approximately equal to the square root of 2. So the difference between exact and approximate answers can come into play. And I think it's worth, you know, it's showing up that this X value on the display looks identical. But when we go to trace and we type in second square root 5, I think I'm saying square root of 2 when I mean
You
square
keep
root of
saying
5.
square root of 2, yeah.
I don't know. My mouth is stuck somewhere that my brain is not. Anyway, but when we type that in here, then it actually tries to put that value into the calculation, and it shows up as being an error or a removable discontinuity or a hole. Even though the hole is infinitely small and you don't see it, the calculator exaggerates the hole when it identifies it in the graph, but it can't find this irrational hole. So anyway, that's a kind of a fun fact uh, when you're trying to do the interface between technology and the analytical math that you often are uh, doing. Let's see. Oh,
And while you're pulling that up, Derek was saying basically the same thing, Greg, that, we have to help students understand that when you see a hole in a graph, that's actually an over exaggerated representation of it. And that's because a hole is infinitely small. And so one fun fact is that the TI-Nspire, yeah, will not show a hole as a hole for that exact reason. But as Phil points out, using the tables, you will be able to see that. Like Greg showed, using the trace, you're going to be able to see where there's those holes. So using these multiple representations, even if visually we can't see the holes, we're going to be able to see them in the tables.
okay, I'm keeping one eye on the clock here, and so I want to get to example 7, and so I'm going to look at example 3, and we're not going to go delve in quite as long in this, but this is a kind of equation that looks so innocent. Natural log of x equals sine of x. These are two basic functions that we study. There's a whole unit in AP Precalculus on exponential logarithmic functions, a whole unit on trigonometric functions. So natural log and sine functions are very fundamental objects for our students to understand. So how would you get started in developing a plan to solve this equation? Go ahead if you've got an idea and put it in chat. Um, what algebraic methods could you use to solve this? Um, what other methods are possible? So you might in chat, if you're answering A, put A in your answer, or if you're answering B, put B in your answer. If you're answering C, put C in your answer. So whichever one of these questions you like best, feel free to answer, or you can answer more than one if you like. But give you a second to think about it. How would you get started on this? What methods could you use?
Greg, we have a suggestion to graph the equations and then look for their intersection points. That trying to find the solutions to this one analytically is going to become very difficult very quickly.
Oh,
Joe says we could use a table to help us understand this. Nana says, let's try out graphing. So it seems like the most popular option right now, Greg, is to pull up the 84 and graph both functions to see where they intersect.
okay, so we might want to use technology for this one. So let's go to our y equals. I think I've got these preloaded, although these would be real quick to enter, right? If it's just a couple of keystrokes to say log or sine. I'm going to make sure I've got other things turned off. Let's see, do I have anything else turned on? Doesn't look like it. Okay. So we're going to graph these two functions, and we've decided that our decimal window is our friend, so I'm going to just go straight for the decimal window instead of monkeying around this time. And we could, it was also suggested that we would look at maybe a table, and we could look at a table too. We got error on this one table. And so let's go back to the graphs and see. It's should be pretty obvious that the pink or magenta is the wavy one, and the other one looks like it's strictly increasing and maybe undefined for negative values and undefined at 0 also. So we've got sine in pink or magenta, and we've got the natural log function. How many points of intersection does it seem that we have here? Go ahead and write it in chat. It looks like there's just one value. And so we could say, what is the intersection? I don't think we used the intersection feature last time, but there's the intersection feature, and it says the first curve. Let's go over here. The first curve is the natural log, and we can see that at the top here where it says y3 is natural log of x. The second curve, and I guess I have to say enter. That I want to use as my first curve, and then I want to use this other one as my second curve. And then for my guess, it looks like it's over here, maybe a little past 2. Looks like somewhere around here, and I'm going to press enter. So the intersection point is most likely an irrational number. And so we would round to 3 decimal places for AP and say it intersects at 2.219, comma 0.797. And is that the arc sine of e to the something? To find an analytical solution would be difficult. This kind of equation, when I first started teaching, was something in your junior or senior year of college when you took a course in numerical methods. And Newton has a method. There's some other methods for finding approximate solutions. But now it's very easy for high school students to find intersections. Now, you could go to the table and kind of do a numerical zoom in and look at what's happening between 2 and 3 and what's happening between 2.2 and so on. But in the interest of time, I think we probably need to move on. I do want to point out that we could come down here and turn on the difference of these two, right? And find the 0 of that function. So I could enter and enter so that we're graphing just the difference of log and sine of x. It's going to be kind of an interesting graph. It's only going to be defined for positive numbers because the log function is only defined for positive numbers. And here, if we wanted to calculate, we could look for a 0 of this one function and press left bound. We'll say, okay, it's somewhere between 1 and 3. And so I think I can just type in 3 instead of tracing over there. Somewhere between 1 and 3, and my guess I'll say is 2. And we still get this same 2.219. And I think it agrees out to all decimal places here. So again, in this case, we did it. We started off with an equation, and we really graphed a system of equations instead of looking at the difference and finding a 0. But there's those two nice ways that you can approach solving equations. And so students will see the connection between systems, and I think the next problem, maybe I should go back and look at the calculator. I think that next question is like, what would the inequalities be? But I'm going to go back to the slide deck and we'll just talk about it. And you can, maybe you're following along on your own calculator and could look at the graph yourself. But for this next, I think I'm going to have to wake my iPad back up. It's had a long day here. Okay. And so, yeah, how could you write the solution? So again, we could take log of x minus sine of x and see when it's positive, negative, 0. And so we could look at that graph, or we could look at the graph of the system and see when is the log functions graph above the sine graph, when is the sine graph below, and we could solve any of the various inequalities, less than, or equal to. So the point here is if you can solve an equation, you can solve an inequality. And so equations, inequalities, and systems, you can see the relationship really well when you do things graphically. If you want to do inverses, the best way to do inverses, I think, is to use parametric mode. So does y equal x squared minus 3 or f of x equal x squared minus 3 have an inverse? If so, could you graph its inverse? Does this function have an inverse function? So there's this subtle difference between inverse function and inverse relation that I think is important for students to understand. And again, I think this is one of the places where the graphing calculator really helps, and what Bert Waits and Frank Domana called the power of visualization. So I'm going to try to go back to my emulator, and let's change the y equals. In fact, I'm going to change the mode, I guess, to parametric mode if we're going to graph parametrically. And so I'm going to enter, and let's see what we've got in y equals. So the way you would graph the natural log would be to do this, but we don't want to graph natural log. I think we want to graph t squared minus 3, I think was the question.
That's correct.
And then we can, again, use this alpha trace to get to the y vars. And notice when we're in parametric mode, it gives you the parametric variables. So that's pretty sweet. And so what I've done here is so that I can change my function and it'll automatically switch x and y. The way we graph an inverse is to switch x and y. Well, in parametric mode, what was x, t is equal to x, and then if t is equal to x, and this is y equals x squared minus 3, and then in the y2 slots, we just reverse those, and let's see what we get. I'm going to check my window. Let me try to graph and see. Whoa, holy moly. We better check the window. We're not graphing anything negative. We want since x equals t, it might be good for us to match up with our x min and x max. So let's make this negative 6.6, which is what the x window is. to positive 6.6. And let's just use a t-step of 1/10. That's our decimal step, right? So that will be compatible with the decimal window, and then we'll graph. Oh my gosh, we're doing parametric, well, parametric representations of conic sections, I guess. So you can have an conic that's oriented in the y direction, and its inverse would be oriented in the x direction. And so there's, I guess, sort of two functions. There's a square root function shifted 3 to the left, and then there's the opposite of that. And so the answer is, does this have an inverse? Yes, but it sort of only has, you have to restrict the domain of the original function to make the function invertible, because the original function would need to either be strictly increasing or strictly decreasing. And that's what we do when we do arcsine, for instance. The nice thing about this is we could switch this to what we had a minute ago, natural log of t, and we could, well, it's erasing everything. Let's try this once more with feeling. Natural log is somewhere. I just saw it. Here it is. Natural log of t. And we'll graph that. And so you have the graph of the function and its inverse. And if you want to see the line of reflection, you can turn on this third set of equations, which is the way you graph y equals x. And then you can see the function, the inverse, and the line of reflection. Okay, well, let's get back to our agenda. We're almost out of time. Maybe you can talk about example 7 just a little bit, Rachel. And then we have to leave a few minutes for the drawing and so on. So hang on here. I'm gonna.
I would never keep anyone from that drawing for a calculator. I know that we're always looking for another calculator for our classroom. Well, while
Okay.
Greg is pulling up the slides, I'll just talk a little bit about it. In just a moment, you're going to see a table. And this was a question that was inspired by a released question in the CED. And I think that's awesome. Thank you. So they say in the CED for this sample question, let f be an increasing function defined on x greater than or equal to 0. And we have this table that gives us values. And then we're supposed to ask, well, what's the best model for this? Do you think it's linear, quadratic, exponential, or logarithmic? And I want to do a really quick pause to have you put your answer into the chat. I'm going to go ahead and ask my next question while you're filling in your answer to part A. But because we are supposed to be analyzing this change in tandem as X does something, what is Y doing at the same time? And so they asked this follow-up question based on the relationship between the change in the output values and the change of the input values. Why are you saying what you said to part A? And then this other major idea that I feel like is new to a lot of pre-calculus teachers, and the stats teachers are just sitting over there grinning because we've spent a lot of time on this, is this idea of justify your reason now using regression and a residual plot. And so I just really quickly wanted to show this. We've got a couple ideas over there in the chat, but I'm going to go ahead and pull this up on the Nspire. There we go. And hopefully y'all can see my screen okay. So I put these values in there, and we had a thought that maybe it was quadratic, but I would like to see this because as I also teach stats, and as a stats teacher, I say, you know what, let me make sense of it by seeing these variables. So I'm going to go ahead and put in my X values. I'm going to put in my f of x values, and these are just straight up from that table. And it looks pretty linear, but there is a little bit of a curve to this one. And so I have a choice. Do I want to try a quadratic? Someone just said in the chat, maybe it's exponential. We haven't really talked about exponential yet. And in the interest of our time, I am going to go with exponential. And I want you to think about those common ratios that you're seeing in the values. So that's beautiful right there. But I want to show something with residuals that I want us to be careful of. So this residual plot right here clearly has a pattern, which is a huge no-no with residuals. But yet, if we do the math, we can actually see that the value of the function when x equals 0 is 3, and that it does have a common ratio of 1.5. So this is clearly an exponential function based on the table, but the residual has a pattern implying it's not right unless you look at the scale. This is one thing I want us to be really careful with. These numbers are basically 0. So even though I have a pattern in this graph, it's because of graphing error. The the exponential regression that we put through these points right here, it just, when it was fiddling around trying to find the best curve, it threw in a little bit of error. So always tell students that we want to look at everything together. We want to look at the residual plot. We want to make sure that we understand what these values over here on the scale for the residual plot mean, and just everything in context. Never just gloss over things where you need to make all the connections. Now, I see it's getting to 4 minutes left in the webinar. So I want to thank everyone for coming on behalf of Greg and myself, and hand things over to Ruth. We've definitely had fun with all of you today, and we appreciate all the participation in the chat. You guys have been absolutely awesome.
Okay. So there's resources, and then maybe this is your next slide, Ruth.
Thank you. Thank you. I almost forgot my job right now. My job is to announce the drawing because I'm looking at that residual plot and oh my gosh. So thank you all for such a great, interesting, intriguing series of examples and opportunity for discussion. All right, so we are going to go ahead with the webinar drawing, and I used random number generator while the class session was going on. The lucky winner is Joseph Blake McDonald. Joseph, congratulations, yay. You'll be getting an email. Somebody will contact you at the email address that you used to register for this webinar, and they'll be asking for your information like which calculator model do you want and where do you want it to be sent. So congratulations, Joseph. Okay, I'm also going to put a link in the chat box. This is going to be a link for the certificate of attendance. All right, let's see if I can actually copy it. It's gonna be in an email that you receive. It might be the one on that slide, or it might be a little bit different, but you will get a certificate of attendance opportunity via email. Also, it's copied in the chat. Don't forget that as you exit webinar, depending on what device you're using, you can save the chat. A lot of great comments, a lot of great ideas, and often some links for you. So depending on how you're joining. I'm also going to put in a link for documents for tonight's presentation. Again, those will be coming to you in email. So following this, you'll get some email at the email address that you used to register, and it will give you a link for certificate of attendance and a link to the documents. Right. That is all that I need to do. There's still a couple, half a minute remaining. If there are any questions or comments that need to be shared in the chat, the panelists would be happy to address those. Thank you both. Thank you, Rachel. Thank you, Greg. And thank you, everybody who joined, for giving of your time and sharing your great ideas and comments.
And thank you, Ruth, for filling in at the last minute because of the snowpocalypse in Louisiana.
Sure. My pleasure.
And stay warm, everyone. I just got the phone call that I have tomorrow off school, so I'll have more time to play with my calculator because now I have more ideas I want to play with.
Thank you. Good night, everybody.
So long.